Welcome back to Pi Academy. This is second video on sequence of function. And in the last video I also told you about when a sequence of function said pointwise convergent and uniformly convergent, and also Cauchy criteria for uniformly convergent. But in this video we learn about MN test for uniformly convergent, and this test is very important to solve any problems related to sequence of function. So what is MN test? A sequence of function fn defined on E subsetter converges uniformly to f on E if and only if Mn equal to sup of x belongs to E mod fn x minus fx tends to 0 as n tends to infinity. If the Mn tends to 0 as n tends to infinity, then the sequence of function converges uniformly, and if the sequence of function converges uniformly, then Mn, where Mn equal to sup of this, tends to also 0 as n tends to infinity. Now the proof of this theorem. The condition is necessary. Let sequence of function fn converges uniformly to f. So we have to show that Mn tends to 0 as n tends to infinity. Let epsilon greater than 0 be arbitrary. Then there exists capital N belongs to the natural number such that fnx minus fx less than epsilon for all n greater or equal to capital N, and for all x belongs to E. This is the definition of uniformly convergent, and we let also fn converges to uniformly converges to f. Now here Mn equal to sup of x belongs to E and mod of fnx minus fx. Since mod of fnx minus fx tends less than epsilon, therefore sup of this also less than epsilon for all x n greater or equal to capital N, and that is, this implies mod Mn minus 0 less than epsilon, since Mn less than epsilon, and for all small n greater or equal to capital N, therefore limit n tends to infinity Mn equal to 0. Now the condition is sufficient. Now let limit n tends to infinity Mn equal to 0. So we have to show that the sequence of function is convergence uniformly. Let epsilon greater than 0 be arbitrary. Then there exists capital N belongs to the natural number set n such that mod Mn minus 0 less than epsilon for all small n greater or equal to capital N, and Mn equal to sup of mod fnx minus fx. Since Mn minus 0 less than epsilon, therefore sup of this, Mn equal to sup of this is also less than epsilon for all n greater or equal to capital N. Since sup of mod fnx minus fx less than epsilon, so it is obvious that mod fnx minus fx less than epsilon for all small n greater or equal to capital N and for all x belongs to E. And this is the condition of uniform convergent of the sequence of function fn, hence the result. Now I discuss about some application of Mn test. Now first application, let fnx equal to x to the power n, 0 lesser equal to x lesser equal to 1. Then the pointwise limit is fx equal to 0 and 1. 0 when 0 lesser equal to x less than 1. Here x less than 1, and 1 when x equal. Now mod fnx minus fx, this equal to x to the power n when 0 lesser equal to x less than 1, and 0 when x equal to 1. Now Mn, we know Mn equal to sup of mod fnx minus fx equal to fnx minus fx when x belongs to E, that is 0 lesser equal to x less than 1, and clearly this is 1 because when 0 lesser equal to x less than 1, then fnx equal to, now sup of this equal to 1 and not tends to 0 as n tends to infinity. Therefore we can say by Mn test that the convergence is not uniform. Now question number 2, prove that the sequence of function fnx equal to x divided by nx plus 1 converges uniformly on 0 lesser equal to x less than infinity. given that fnx equal to x divided by 1 plus nx, where 0 lesser equal to x less than infinity, it is given. And the limiting function is fx equal to 0. Clearly when n tends to infinity, then something by infinity equal to 0, where 0 lesser equal to x less than infinity. Now mod fnx minus fx, here fnx equal to x divided by 1 plus nx and fx equal to 0, and this equal to this, and we say this as gnx. Now gn dash of x, now derivative of this v constant, the derivative of u, minus u constant derivative of v by v square, and this equal to this, and clearly this is, since it is square, therefore it's clearly it's greater than 0 for all x. Therefore gn is strictly monotonic increasing on the interval 0 comma infinity. In this interval we can say that since gn dash x greater than 0, therefore gn is strictly monotonic increasing. Therefore the supremum exists when x tends to infinity. Now sup of 0 lesser equal to x less than infinity, gnx equal to limit x tends to infinity, gnx equal to limit x tends to infinity, x divided by 1 plus nx, and this equal to 1 by n. When if we divide this by x, that is we can write 1 divided by 1 by x plus n. When x tends to infinity, then it gives 1 by n. Thus mn equal to sup of mod fnx minus fx. This is clearly 1 by n, because the supremum value of this, a supremum of mod fnx minus fx equal to gnx say. Therefore the value, the sup value of gnx equal to sup value of this. Therefore supremum value of this equal to 1 by n, and which tends to 0 as n tends to infinity. Hence therefore by mn test the convergence is uniform, because mn test is the necessary and sufficient condition for uniform convergence of sequence of function. And that's all. Thank you for watching. Please like, share and subscribe my YouTube channel Pi Academy, and hit the bell icon to get all the notification of my new videos. Thank you once again.